In Chapter 5, we'll talk a little bit more about early atomic theory and atomic structure. So let's talk about Dalton's model of the atom. So the first theory that we have, Dalton's theory, is proposed in the early 1800s. It states that number one, elements are composed of small particles called atoms. They're the smallest there is. And atoms of the same element are going to be identical in mass and size. And it also says that atoms of different elements will differ in their mass and size. So basically, a different element will have atoms that are a little bit different. Compounds are then formed by combining two or more atoms of different elements. Atoms combine to form in simple whole number ratios. So 1 to 1, 1 to 2, 2 to 3, just whole number ratios. Number 6, atoms of two elements may combine in different ratios, leading to formation of different compounds. For example, like we have CO2, it's different from CO. So let's take a look here. These are atoms, individual atoms. We have O, H, H, O. All these are separate atoms here. And then we combine them. We can make, from these guys, we can make H2O. So 2 hydrogen to 1 oxygen. Or we can make H2O2. So this is water, and this is hydrogen peroxide. But they're all made of still H and O. It's just that we combine in different fixed ratios. Most of the theory from Dalton's theory still remains valid today. So some revisions, basically things that we've learned that's not completely true. So basically atoms can actually be, elements can be decomposed under certain conditions. Number 2, that not all atoms of the same element will actually have the same mass. These are called isotopes. So before this, Dalton just assumed everybody's going to be the same. Now we learned that within one type of element, we actually have isotopes. So the masses are going to be a little bit different. So atoms are not indivisible. Atoms are actually composed of subatomic particles. So we thought, well, Dalton thought that atoms were the smallest thing ever. That's it. But now we know that atoms are actually comprised of subatomic particles, which are, we will talk about protons, neutrons, and electrons. So speaking of electron, let's talk a little bit about electric charge. So the properties of charges, it can either be positive or negative. And then obviously opposite charges will attract, like charges will repel. And then charge can be transferred from one object to another by contact or by induction. We don't need to worry too much about it. You really need to just focus on, we have positive or negative charges, and opposites attract. The same charges, they repel each other. So here's the formula for force of attraction between charges right here. We don't need to worry too much about that. It's just there to show you that there's a formula. And then like we want to talk about also in this formula, Q1 and Q2 are the charges, R is the distance between the charges, and K is the constant. We won't be doing calculations with it, but it tells you like in a certain distance, at some point their attraction is stronger than at other points. So let's talk about who discovered ions. So Michael Faraday, he's an English scientist who discovered electrolytes. So basically compounds that conduct electricity when you dissolve them in water. Faraday also discovered that some compounds decompose in water into their elements. And actually, these elements were either negatively or positively charged. And then so they were attracted to a negative charge or a positive charge electrodes in the solution. So they weren't neutral. So let's see a picture here. You see how the light bulb goes on here within the solution? It's because in the solution here, there are electrolytes that are positive charge or negative charge. So the positive ions will be attracted to the negative electrode, and the negative ions will be attracted to the positive electrode. So these things, we call them ions, the electrolytes. So it says here a light bulb glows when ions are present in saltwater solution when the current is passed through it. So based on Faraday's work, Arrhenius did a little bit more work. He proposed that ions are atoms or groups of atoms that carry a positive or negative charge. So NaCl in water dissociates into two ions, Na plus and Cl minus. Na plus is called a cation because it's positive charge and it's going to be attracted to the negatively charged electrode. We call that cathode. The Cl ion, in this case anion here because it's negatively charged, is produced and it's attracted to the positively charged electrode. So it's just opposite charges attract. So based on Faraday's and Arrhenius' work, Stoney then proposed that electron was a fundamental unit of electricity associated with atoms. J.J. Thomson later experimentally confirmed the existence of electrons. So he did an experiment in a cathode ray tube that confirmed that electrons are there. It's not just a theory. So let's talk about a small tiny atom. It's super tiny. The diameter is between 0.1 to 0.5 nanometers. So remember nano is 10 to the minus 9. So it's really small size. Because atoms are so small, determining presence of subatomic particles was really difficult, especially back then. So new instruments in an early 1900 allows detection of these particles. For example, if we use scanning tunneling microscope, STM, it shows an array of copper atoms, so we can start seeing a lot finer details. So here's the cathode ray. This is kind of like the basic foundation of what J.J. Thomson used to discover electrons. So the cathode ray here is a stream of electron, and they notice that it's attracted to, so electrons are attracted to the positive side and it's repelled by the negative side. And if you put like an electric field or a magnetic field on it, it'll actually bend the electron beam, the cathode ray, indicating it has a charge. So if it was like a negative field, it will go away from that field. If it's a positive field, it will go towards that field, since it's a negatively charged electron. Alright, so we talked about electrons, how electrons have negative charges. So we'll call electrons with negative charge, we assign them a relative charge of -1. And it's very small mass. So it's 9.11 times 10 to the minus 28. That's super small, -28, 10 to the power -28 grams, and a size of smaller than 10 to the minus 12 centimeters. So it's really small, okay? One thing you gotta remember, our relative charge of electrons is gonna be -1. So each electron is -1 charge. Protons is going to be positive charge, and we assign a charge relatively called +1. So each proton is +1, and protons have a much larger mass, so it's almost 2,000 times heavier than an electron. So we always consider protons having a mass, and electron will be kind of like no mass because it's so small. Now, so Thomson's work demonstrated that the atom is composed of smaller charged particles. Dalton's theory then had to be revised again. So again, theory is only true until someone proves it wrong. So let's keep revising it. So Thomson has a new model. He thinks that since they found electrons, they're negatively charged, and it's embedded in a positively charged atomic sphere. So it looks like this. Like, obviously, this is not this the model that we have right now, because this one is also proven wrong. So this model is called the plum pudding model. They have a lot of plum pudding in England, so that's why it's like common for them. If it was like an American scientist, we might have called it like the blueberry muffin model, okay? Because there's like these little blueberries in there, evenly distributed, and the muffin overall is a positively charged atomic sphere. Now, so that was the theory they came up with since they found electrons. And the next thing is, let's talk a little bit more about cations and anions. So cations are positively charged, right? How do you get a positive charge? Is when you have an atom and it loses one electron. So take away, so atoms are neutral charge, no charge. So 0, take away -1. So 0 minus -1, you get +1 charge. That's how you get a cation. Now anions are the opposite because you have to gain electron. So from an atom here is neutral, is 0. You put an electron in, so 0 plus -1, your charge will be -1 charge right there. And here's another example of cation with 3 electrons being lost, so it's +3. Here's an example of another anion with 2 electrons being gained, so the charge is -2. So depending on how many electrons it gains or loses, that's how you tell what charges they have. So neutrons are the last piece of the puzzle. So we so far talked about electrons and protons and how electrons can actually help an atom change to ions. And then protons are +1 charges. Now we want to talk about neutrons. Neutrons is the reason why we have isotopes. So this was discovered by Chadwick in 1932. It's a particle with no charge, but it has a mass similar to a proton. So neutrons, no charge, okay? So in this case, we have electron. Our symbol is E negative, charge of -1. Mass is super, super small. Proton will be about 2,000 times bigger or heavier than the electron. So, and the neutron and proton weigh about the same. Okay, so 2,000 times heavier. And charge for a proton is going to be +1. Symbol is called P, neutron is called N symbol, and no charge, 0 charge, neutral. So Ernest Rutherford, he was working for J.J. Thomson. Remember Thomson was the one that talked about the plum pudding model or the blueberry muffin model. And he wanted to prove Thomson's theory correct, actually, but when he was doing his experiment, he accidentally proved Rutherford proved Thomson wrong by accident. So what he did was he used a source of alpha particles. At that time, radioactive particles are really common. They were learning about it. So he used alpha particles, radioactive particle. He shot a thin gold foil, which has a lot of gold atoms in it, and he expects it to actually all just go straight through. Because if it goes straight through, that means it was like the plum pudding models where the electrons can just go through all the empty space that they have. But what he observed was not what he expected to see from the plum pudding model. He sees that instead of all just going straight as predicted, some of them turn around, some of them actually make a U-turn. So there's something else in there blocking the alpha particles because alpha particles are positively charged. For it to move instead of going straight through, that means there's something positive somewhere in the middle. So it's if it hits the middle, it turns around like a U-turn because it's completely positive. Sometimes it hits the corner of the middle, it sort of just deviates from its original path. So he had to come up with a new model. So his new model is going to have something in the middle that's positively charged, which is. So the new model now for Rutherford means that there's a nucleus in the middle, and in your nucleus there's going to be neutrons and protons, which is why it's positively charged. Actually, at the time that Rutherford did this experiment, they didn't even know neutrons were there yet, but they just knew that there was some extra mass but no charge. So Chadwick put together the neutron piece, so then this is the final picture that we have. But Rutherford basically said our nucleus is going to be positively charged. Okay, so the protons are going to be inside the nucleus. That's what he knew, and he didn't know what these things were. They were still hypothesizing what the neutrons were at that point. And then around it will be our electrons, where it's negative charge. So positive can go through negative straight through, and then if it hits something positive with the alpha particle, it will deflect, go backwards or turn around. So this is the current model that we know of. Let's talk about atomic number. Atomic number is the number of protons inside the nucleus of an atom. So atomic number determines the identity of the atom. So if you have a certain number of atomic number, that's the identity. Anything that has a different number of protons will mean it's a different element. So if it says 27 on a periodic table, that means it's cobalt, because cobalt always have 27 as the atomic number, or 27 protons. If you change it to 26 or 28, it will be no longer cobalt. It will be a different element. So we were talking about how each element has different masses, right? Because of the isotope. So we found out that the mass of almost all atoms were found to be larger than expected based on the number of protons and electrons. See how they were like, okay, we know protons are in the middle and electrons are on the outside, and that's why we know there's neutrons, because neutrons add to the mass but not to the charge. So even though atoms of the same elements have the same protons, remember if it's a different proton, it's a different element altogether, the atoms of the same element can actually have different numbers of neutrons. Okay, so they have different neutrons but the same protons. That makes them isotopes. So that means they have the same atomic number, because atomic number means number of protons, but different number of neutrons. And you see that if you later on we'll talk about how neutrons plus the number of protons gives you a mass number. So for example, we have hydrogen. We want to talk about isotopes of hydrogen. If we have 1 proton and 0 neutrons, we call it protium. You see how there's a 1 on the top and then H and then 1 on the bottom. So the 1 on the bottom tells you how many protons. The 1 on the top tells you the total of protons and neutrons, which is 1 plus 0, so equals to 1. Now deuterium is going to be 2, 1, H, because there's 1 proton that goes on the bottom and then another neutron. So now the 2 on the top there is a mass number. It's called mass number because it's 1 proton plus 1 neutron gives you 2. And if you have 1 proton and 2 neutrons, gives you 3 on the top and 1 proton on the bottom. So you see here, because it's 1 proton on the bottom, all of these symbols will have H as a symbol, the element, because it's hydrogen isotope. And then within these 3 guys here, we have different number of neutrons, so we have 3 different isotopes. So don't forget, mass number goes on the top, the bigger number goes on the top, atomic number is just a proton that goes on the bottom, and the symbol of the element goes on this side, on the right side. So on the top is the mass number, big number. The bottom is atomic number, which is just the protons. And remember, mass number is the number of protons and neutrons added together. So here's some more examples of determining the number of neutrons. So if you have hydrogen 1,1H, that means there's 1 proton for H, and then there's no more neutron because it's 1 plus 0 to get 1. Okay, so there's no neutrons there. And then if you have oxygen, the number of protons is 8 for oxygen, and then you have 16 of the mass number. So that means 16 minus 8 will give you the number of neutron, which is 8 right there. If it's sulfur, it's 32 mass number minus 16 atomic number. That means numbers of protons and neutrons minus number of protons will give me the number of neutrons. And then fluorine here is 19 and 9. So that means you take 19, which is the total protons and neutrons, minus the protons. You get the neutrons left over. Same case here, 56 minus 26, you get 30 for the number of neutrons for iron. So let's practice identifying the number of subatomic particles. So we have Cu here, okay? Cu is copper, and it says 64 on the top, 29 on the bottom. How many protons are there? So number of protons will be 29, okay? Number of neutrons will be 64 minus 29. And then number of electrons, electrons, if this has no charge, that means the atom is neutral. electrons and protons will be the same number. So it will be 29 as well. So in this case, our atomic number is 29 because there's 29 protons. So 29 right there. And then therefore 29 electrons because it's not charged. And then we have number of neutrons. We mentioned it was going to be 64 minus 21. We have 35 for neutron. Next question. Which isotope corresponds to an element with 24 protons and 28 neutrons? So you need 24 on the bottom. And you see that's the only option, 24 on the bottom. And then 28 neutrons means 24 plus 28, which is 52, it goes on the top. So our answer should be 24 on the bottom, 24 plus 28 on the top. And then if you look on the periodic table, number 24 is Cr, chromium. A little bit more about atomic mass. Because the atom is so small, the mass is really small, as we saw earlier. So we want to go ahead and use something that's a relative unit. We call it atomic mass unit. It says U here. Sometimes I write AMU also. So sometimes it's written as AMU, atomic mass unit. Okay, so one atomic mass unit is about 1.66 times 10 to the minus 24 grams. So that equals to one atomic mass unit. If you look back at the chart earlier, so this will be pretty close to the mass of a proton and a neutron. So that's what we're going to use. So how do we come up with this number? It's because we use carbon 12, which is 12,6 carbon. That means the carbon has 6 protons and 6 neutrons as the standard. So one atomic mass unit is equal to 1/12 of the mass of a carbon-12 atom. So they took this 12,6 carbon divided by 12 and they get this number, which is pretty darn close to the mass of a proton or a neutron. The whole entire periodic table uses atomic mass based on the carbon-12 isotope. So if we say 1 AMU, it's just 1/12 of the carbon-12 number. So since we talked about atoms having different isotopes, and obviously each isotope weighs a little bit different, we want to start talking about the distribution of these masses according to how much isotopes there are. So we usually do the atomic mass for the element that you see on the periodic table, and it's going to be a weighted average of all the naturally occurring isotopes for that particular element. So we can talk about whatever element. Sometimes there's 2, 3, 4, 5 isotopes, but a lot of times like one of them is the most common form, and then some of them are not as common. So that's why we need a weighted average formula. So if we say we want to take a look at copper, the atomic mass of copper, if you see on a periodic table, is 63.546 AMU, atomic mass unit, and copper exists as two major isotopes, which is copper 63 and copper 65. So copper 63 is more abundant, and so the atomic mass is very close to 63 because it's close to the mass for copper 63. And then we have the other isotope, which is copper 65. It's a smaller amount. So to calculate the average atomic mass, we want to multiply the mass of AMU of each isotope by its percentage abundance. And the percentage abundance, if you write it in a fraction, it's basically a number smaller than 1. You take the percent abundance divided by 100. So in this case here, we have copper 63 and copper 65, and AMU for copper 63 is 62.9298. For copper 65, it's 64.9278. So these are the AMUs of the individual isotope, and you can see that 70% of them is going to be the copper 63. So this guy has a lot more impact It happens more common than this one. This one's only 30% of the time. So when you take an average of these occurrence plus the individual masses like that, the average comes out to about 63.55, which is closer to this number, which is 63 instead of the 65 number. So how do we measure these isotope abundances? So the formula is, remember, we say the atomic mass, the AMU, times the abundance, and the abundance I mentioned is a percentage, but you divide it by 100 to get a number, a fraction out of 1, so 0.6909 for 69.09%. And then this is the AMU for the second isotope, which is close to 65, and the abundance of the second isotope, which is 30.91%, so we write it as 0.3091 as a fraction of a number, so you get an answer of 63.55. And if you take a look, if we did mass spectrometry of copper isotope, you shot copper in and you see the sample, 69% of it is going to be around a 63 mass, and then about 30% of it is going to be at 65 AMU. So let's practice calculating for silver. It has two isotopes naturally occurring with atomic masses of 106.9041 AMU and 108.9047 AMU. Remember, this U is AMU, atomic mass unit, and it says determine the average atomic mass for silver if the percent abundance for each isotope is 51.82% and 48.18% respectively. So you see here, 51.82 plus 48.18, it adds up to 100. Because if you know, like, the total is going to be 100%, if one isotope is 51.82, the other one is going to be 100% minus 51.82 to get 48.18%. So sometimes in the question, when they give you just one percentage and they say there's two isotopes, you take 100 minus the original percent, you can get the percent of the second isotope. So let's go over our formula again. So our formula is going to be abundance number 1, 5182, times mass number 1, which is this guy right here, and then abundance number 2, 4818, times the mass of the second guy. So you take the abundance times the mass plus the abundance times the mass, and you get an average number of 107.8680 AMU. So as you can see, it's almost 50-50, so the number comes up about right in between 106 and 108.9. 107.8, yeah, it's kind of smack in the middle almost, because they're almost 50% each. Let's do one last question. So in this question, chlorine exists as two isotopes, chlorine Cl37, AMU of 36.96590 atomic mass unit, and Cl35. If the percent abundance of the first isotope is 24.47%, what is the atomic mass of the Cl35, which is the second isotope, if the average atomic mass is 35.46 U, which is AMU? So let's take a look at how we would do this. We would take the abundance of the first one, which is, so abundance times the mass, right? So you can write down 36.96590 AMU times the abundance of the first one, which is 0.2447. Okay? And then you got to add with the second mass, which we don't know what it is, so I'm going to call it X. Okay, so this is where algebra comes in. And then the abundance of the second one is going to be 100% minus 24.47%, right? Or 1 minus 0.2447. So if you do that on a calculator, you see 1 minus 2447, you get 75.53. So I'm going to write 0.7553. Okay, now remember, this is from getting 1 minus 0.2447. That's how we got this number right here. Okay, so once you put that in, This should equal to 35.46 AMU. So what you want to do to solve for x is you would have to calculate x as in this case, we want to do 35.46, and then you have to minus the product of the first term here, which is whatever 36.96590 is, times 0.2447. Okay? And then you also have to get x, you have to divide by 0.7553. Okay, so when we get the answer here, it's gonna give you a long list of number based if you just go straight in your calculator. You get maybe like in this number here, you get up here, you probably get something like 9.046 right here on this top number. Okay, and then you 35.46 minus that number and then divided by 0.7553, you should get something about this number. So 34.97212. So you see here, it doesn't really show up there, but because we're stuck at two numbers here, two decimal places, that's the smallest sig figs. We have 4 sig figs here. So we will actually stop right here. So it's 34.97. So let's just take a look and see, is there anyone that will say 34.97? See, this is the only one that's really close. Our answer here should be D. All the other guys aren't even close at all. So that's how we would do that. If you have trouble with algebra, make sure you brush up on it. And we can also work this in class some more and make sure you ask questions.